Hi, welcome back. Let's begin by recalling the main proposition that we want to prove. This is lecture 4. So the proposition that we want to prove is proposition 8. So the setup is we have a Noetherian integrally closed domain we let K denote its fraction field and we had a finite separable field extension L over K. And we let B denote the integral closure of A in L. And the conclusion is that B is a finitely generated, which I abbreviate by f dot d jot. So it's a finitely generated A module. So just as a field diagram, we have A sitting inside K, which sits inside L, and inside L is this B, which contains A. So let's go to the proof. So since A is Noetherian, so it will suffice to show that B is contained in a finitely generated A module M. This is because, if you recall, since A is assumed to be Noetherian, a finitely generated A module M is a Noetherian A module, and hence every A submodule of M is also a finitely generated A module. Okay, so since we're working with the hypothesis that A is Noetherian, to conclude that B is a finitely generated A module, it's sufficient to embed it inside a finitely generated A module. Okay, so that's our goal. Now, how do we do that? So let's first use the hypothesis that L over K is finite. So we choose a K basis. Let's call it W1 up to Wn of L over K. And we had this lemma phi of clearing denominators. So by clearing denominators, we'll assume we may assume that each of these Wi, they're integral over A, that is, each Wi in fact belongs to B. So we have the hypothesis that L over K is finite separable, so we need to use that. So since L over K is finite separable, recall from the previous lecture that the trace map from L to K is a non-degenerate K linear map. What does non-degenerate mean? There exists an alpha naught in L which is non-zero, and moreover it has the property that its trace is not zero. Okay. So what does this buy us? So we obtain a k-linear map, that is a map of k vector spaces, as follows. So I'll call that map sigma. It's from L. So L is a k vector space. So I can think of all the k homomorphisms from L to k. So these are just vector space homomorphisms over k. So it just sends x to a homomorphism. Let's call it phi x. And how is phi x defined? It's a homomorphism from L to k, and it's defined. So if you give me an element alpha, it should depend on x as well. It should depend on alpha. I multiply x and alpha in L and then take the trace. Okay, so now observe that sigma is k linear. And why is that? Well, if you give me two elements in L, then we claim that sigma of x plus y equals sigma of x plus sigma of y. Why is that? So the left hand side, which is sigma of x plus y, by definition is the map phi of x plus y. And how does this map work? For all alpha in L, we have phi of x plus y applied to alpha This is the trace from L down to k of x plus y multiplied by alpha. And if you recall how the trace works, you look at the distinct embedding sigma I from L to its separable closure, and you apply it to x plus y times alpha. But since these sigma i's are field embeddings, you can write this as the sum 1 to n of sigma I of x alpha plus the sum 1 to n of sigma I of y alpha. But each of these is the trace from L to k of x alpha plus the trace from L to k of y alpha, which by definition is phi x applied to alpha plus phi y applied to alpha. So for all alpha in L, we have that phi x plus y applied to alpha is phi x applied to alpha plus phi y applied to alpha. So this gives phi x plus y as a map equals phi x plus phi y inside harms the k vector space harms from L to k, and thus what we get is that sigma of x plus y equals sigma of x plus sigma of y. And now to show that it's k linear, we also need to show that if you take an element, call it x, in L, and you take a scalar called a little k in the field K, then what we need to show is that sigma of kx equals k times sigma of x. That is, what we need to show is that phi of kx equals k times phi x. But again, evaluating the left hand side, so this map phi kx applied to alpha is nothing but the trace L over k of kx alpha, but the trace function is k linear, so you can pull out the k, and so you get k times phi x applied to alpha. And so this is enough to show that phi kx equals k times phi x inside the homomorphism group of k vector spaces from L to k over k. Okay, so thus what we've shown is that this map sigma from L to harm L to k as a k, when we look at all the homomorphisms as k vector spaces, this is a k linear map. So we want to investigate this map sigma. So our first claim is that sigma is injective. But since it's a k linear map, it's enough to check injectivity. So to prove injectivity, it's enough to check that the pre-image of the 0 map has cardinality 1. So there's only one element of L that maps to the 0 map. And this is sufficient because we're using the fact that sigma is k linear. And so clearly under sigma, the element 0 maps to the 0 map in harm L to k, and so we need to show that no other element of L maps to the 0 map. So suppose, for the sake of contradiction, there exists an x that's non-zero in L such that phi x is the 0 map. In all the k linear homomorphisms from L to k. However, we had this distinguished element alpha naught with the property that its trace was non-zero. So if you evaluate phi x on this ratio, alpha naught over x, you get that it's, by definition, it's the trace from L to k of x times alpha naught over x, which is the trace of L to k of alpha naught, which was non-zero, but by assumption that since L over k is finite separable, the trace function we had that the trace function is non-degenerate. Okay. So this is a contradiction. Since by assumption, so we argued by contradiction, our sigma x was a 0 map, but then we have this element alpha naught over x that maps to non-zero. Okay, so this provides the contradiction, and this proves claim A. That sigma is injective. Now claim B is that sigma, which is this map from L to k-linear homomorphisms from L to K, is in fact surjective. And again, why? So this uses the fact that an injective map of K vector spaces with the same dimension is in fact surjective. Okay, so here L as a vector space over K is n-dimensional. So this has dimension n over K. And the basis, so we had one choice of basis, W1 up to Wn. Okay, but this Harm space from L to K, the set of k-linear homomorphisms from L to K, this also has dimension n. And so if you fix a basis W1 up to Wn of L over K, we have a dual basis. I'll call it delta W1, delta W2 up to delta Wn. And how are these delta Wi's? How are these maps from L to K defined? So you write an element alpha in L as a linear combination of the Wi's. So C1 W1, C2 W2 plus Ci Wi plus dot 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 Cn Wn. So here the Ci which belong to K are the coefficients of the basis vector Wi. And hence it's, since W1 up to Wn is a basis for L over K, these coefficients Ci they're uniquely defined. They're uniquely determined by the basis W1 up to Wn. And so this map delta Wi acting on alpha by definition is Ci. So it picks out this coefficient Ci of Wi. And so in particular, if you evaluate delta Wi on Wj, you get that it's 0 if I is not j, and it's 1 if I equals j. Okay, so this proves claim B that sigma is surjective, because you have an injective map of K vector spaces with the same dimension. We're calling the dimension n here. Okay. So now you choose you have this map sigma from L to the homomorphism group of L to K. So inside the homomorphism group L to K, we had this dual basis delta W1, delta W2, and so on and so forth, delta Wn. So you pick, so we see that sigma is both injective and surjective, so it's an isomorphism. So you pick W1 up to Wn, or sorry, V1 up to Vn, which is a basis of L that maps to this dual basis. Okay, so under sigma, so you pick V1 up to Vn, which is a basis of L over K, with the property that sigma of Vi maps to delta Wi. Okay, and so sometimes by abuse of notation, this basis V1 up to Vn is also called the dual basis with respect to W1, Wn, when keeping in mind the trace function. Okay, by this lemma on cancelling denominators, so we can actually find a Ci for each of the Vi, which is non-zero in A, such that the Ci Vi is integral over A. And since okay, so now let C denote this product C1, C2, Cn. Since each of the Ci's are not 0, this product is also not 0, and it's in A. So our last claim is that this integral closure, so remember that B was defined to be the integral closure of A in L. Last claim is that it sits inside a finitely generated A module, but the module is generated by W1 over C, W2 over C, and so on and so forth, Wn over C. And so why? So you take an element in B and you write it down in terms of the basis vector W1 up to Wn. So you have D1 W1, D2 W2, so on Dn Wn, with the property that the coefficients D1 up to Dn, they belong to K. Now, if you multiply by Cvi on both sides, then what do we get? Well, notice that Civi is integral over A, and C is just a product of Ci with a bunch of other elements that are in A. So Cvi is also integral. So the Cvi, this is integral over A. So on the one hand, we have Z times CVI. You're multiplying Z, which is in B, so it's integral over A. You have CVI, which is also integral over A. So this product is integral over A. So on the right hand side, we have D1 CVI W1 plus D2 CVI W2, so on and so forth, plus DI CVI WI, plus so on and so forth, dn CVI Wn. And now if you take trace, and using the fact that trace is k-linear, so we have trace from L to K of Z CVI is the sum, as j goes from 1 to n, of trace L to K of D dj CVI Wj. Okay, but just the way Wj's and the Vi's work, so this just picks out the coordinate I. So we have summation j equals 1 to n. You can pick out the dj, you can pick out the c because the trace function is k-linear, and then you have trace L over K of Vi times Wj. But this is nothing but delta Wi of Wj. And just the way these delta functions work, you just get the coordinate, you just get 1 when I equals j. So it picks out dj, di times c. But on the other hand, since Z CVI is integral over A, the trace of Z CVI should also be integral over A. So on the other hand, by corollary 7, the trace of ZCVI actually belongs to A, since we are also using the fact that A is integrally closed by hypothesis. Okay, so combining these two observations, we have that DIC is in fact an element of A. Okay, so write DIC equals AI, which belongs to A. Okay, and what this means is that the DI is AI over C. And so our element Z, which was D1 W1 plus D2 W2 plus so on and so forth dn Wn, if you write it in terms of the AIs, you get A1 over C W1 plus A2 over C W2, so on and so forth, AN over C Wn, which is nothing but A1 times W1 over C plus A2 times W2 over C plus so on and so forth, AN times Wn over C. And so this tells us that this element, this arbitrary element Z of B, in fact belongs to A, this module over A generated by W1 over C, W2 over C, and so on and so forth. Okay, and so this is enough to prove claim C. And so thus we have that B sits inside this finitely generated module over A, So let's call the right hand side as M. It has the property that this is finitely generated as a module over A with generating set W1 over C, so on and so forth, Wn over C. And so you can embed B inside a finitely generated A module. And since A is Noetherian, this is enough to show that B is a finitely generated A module. And this completes the proof of the proposition. Okay, and this ends lecture 4. Thank you.